Solubility. I'm going to try and introduce to you some ideas to do with solubility. Let's start with some water as a solvent. Here I've got distilled water. Now, distilled water is about the purest kind of water we have in chemistry laboratories. We boil tap water, turns into steam, we cool the steam down. That's distilled water carried out by simple distillation. And if I just show you here, so water as a solvent will dissolve something like sodium chloride. Sodium things, potassium things, ammonium things dissolve easily. So if I get a little bit of salt, sodium chloride, and if I put it in there and with a glass rod, I can show you when I stir it, you can probably see the little pieces floating around. You see the little pieces floating around there? And as I stir it, those pieces get smaller and smaller and smaller until they completely break up. And that's salty water. It can dissolve more salt than the amount of salt I put in there because the solubility is more. I've not exceeded the solubility. If I exceed the solubility, then the solution will be saturated, and if the solution is saturated, I won't be able to get any more salt to dissolve in there. And I have a Bunsen burner. So if I really want to dissolve something quickly, I would warm up the water. Now, I want to get some water being warmed up. This is distilled water. I'm going to warm that up. Now, solubility curves. Solubility curves tell us how much solute dissolves per 100 gram of solvent. Now, look at my previous video and I'll take you through these ideas theoretically there. This is an opportunity for us to show you some practical. Where things dissolve, we have to stipulate how much solvent to take. And the internationally agreed standard is to take 100 grams of water. So I've got some solute here. I've got some ammonium chloride. Look. Ammonium chloride, and I've weighed out using a 2 decimal place balance. I weighed out exactly 2 grams. So I've got 2 grams of ammonium chloride. Now, if I take a thermometer and a boiling tube, and I've got a little measuring cylinder here. The measuring cylinder, I can measure out 5 centimeter cubes of distilled water. So carefully, if I put distilled water in there, I've got far too much. I need to pour out some, and I've poured out far too much. I need to put some more back in. A few more drops. I'm about half a centimetre over. So just take that out. I've just gone under, just gone over. Just over again. Just under. Sorry guys, maybe I should have got 5 ready before I started the demo. But I'm trying to get 5, I keep going under and over. There. So, I wanted to show you, that is 5 centimeters cubed of distilled water. Now if I put that in there, 5 in water in there, together with 2 grams of ammonium chloride, 2 grams of ammonium chloride, that's that solid there. The way I can do that is to do a little crease and to put that in there like that, and to try and dissolve it. Now, ammonium chloride in water, I can try and dissolve it. I can get a glass rod and I can stir it all up, and it won't dissolve all of it. It won't dissolve because I've exceeded the solubility at room temperature. But what if I had hot water? Well, that's what that's about. That water's boiling, so I'm going to turn that off. That water boiling, put this in there. The boiling water will warm up my test tube. It'll warm up the test tube, and I'm hoping that the ammonium chloride will all dissolve. See? It's dissolving. There's some ammonium chloride towards the top end, so just going to try and get that in. Can you see? There, I think the ammonium chloride has all dissolved. Now what we do is we put a thermometer in and we put it in there, and now we look. We look to see when that mixture forms crystals. And we look at the temperature. At the moment, the temperature is 53 degrees. If we leave it, it'll cool down. As it cools down, the solubility of ammonium chloride will get less and less and less and less. And by the time it reaches room temperature, then that amount of water, as you saw when we started, that amount of water won't hold and be able to dissolve 2 grams of ammonium chloride. At some temperature, we're going to see crystals. And that's the temperature I'm hoping to record. The temperature at which we get crystals. And when they start to form, hopefully, I will be able to show you the crystals. So I'm just going to keep an eye on that while I talk about another idea, and we'll just wait for the crystals to form. And believe it or not, this waiting for crystals to form is called crystallization. So that's crystallization. I'm waiting for crystallization to happen, and the crystallization will give me crystals of ammonium chloride. But the temperature has to get colder and colder and colder for it to do so until temperature is low enough for the solubility to be exceeded and for the solution to be saturated. At the moment, the solution is not saturated. That's why we're not seeing any crystals. So just going to keep an eye on that. Now, iron brew. Let's talk about this. That's better. Right. I want to talk about dissolving gases into a solvent. Now, all too often, we talk about dissolving solids, but carbon dioxide is a gas. And how do we make our drinks fizzy? We make them fizzy by putting carbon dioxide into fizzy drinks. If I shake it up, see those bubbles? Those bubbles are bubbles of carbon dioxide. We could prove they were carbon dioxide by, if I put a cork with a tube, shake it up and bubble the bubbles I get through lime water, the lime water would go white precipitate. The white precipitate would be calcium carbonate, proving the bubbles are carbon dioxide. I'm not going to do that. I just want you to trust me that carbon dioxide, fizziness in fizzy drinks is produced by carbon dioxide. And those of you that have heard of a device called soda stream, a soda stream takes little cartridges of carbon dioxide gas, and those tiny cartridges of carbon dioxide gas, they bubble carbon dioxide through the drink, turning it into a fizzy drink. And that fizziness is what gives you the texture of a fizzy drink. And carbon dioxide is acidic, and the acidity gives it a sharp flavour in your mouth. People like that, and therefore they drink fizzy drinks. My brother drinks fizzy water. Personally, I can't stand fizzy water. But he likes the flavour of the acidity caused by the carbon dioxide gas, and he likes the bubbles in his mouth, and a personal taste, I suppose. So, gases can dissolve in water in the same way that I've been dissolving ammonium chloride, or I've been dissolving sodium chloride to make salty water, and ammonium chloride solution. An iron brew is not just water, but largely water with carbon dioxide bubble through it under pressure, and then top put on to keep the carbon dioxide in the bottle. Okay, while this is still cooling down and it's not started to make crystals yet, let's show you another demonstration. Now, another demonstration is this one here. I might have to move it away. Maybe I could show you like this. This is water with a drop of sulfuric acid and a few drops of phenolphthalein indicator. No, actually, no, not phenolphthalein indicator, universal indicator. Universal indicator with a drop of sulfuric acid makes that bottom flask red. The bottom flask is attached to the top flask, and the top flask is full of ammonia gas. That's got ammonia gas in it. Now, ammonia gas is a very, very, very soluble gas. That gas is very soluble. It dissolves in water very, very easily. And look, that, if I open this tap, that's connected to this. I'm going to open the tap now. Well, not now. Let me explain it first, because it might happen rather quickly. When I open the tap, I might have to blow to get a little bit of the water coming out the end. But when a little bit comes out, then the ammonia should dissolve into the water, and as the ammonia dissolves, then there's less ammonia in that top flask. That top flask will have a suction effect. Top flask will have a suction effect, and the water from the bottom flask will get sucked. Sorry, I think my hand turned off the recording there, but I was trying to say the bottom flask water will get sucked into the top flask water if it dissolves into it. Now, I'm just going to do that so you can see it. I hope you can see it there. And The other thing about indicator is that the ammonia is an alkaline gas. So this is red because it's acidic. When it goes up into here, being an alkaline gas that dissolves, when all this gets sucked up, the indicator should go blue. This is called the fountain experiment. I'm going to open the tap that connects the two together, the bottom flask to the top flask, and then I'm going to start the fountain experiment by blowing. Can you see? The bottom flask is getting less and less and less and less. The top flask is getting more and more and more. Can you see the fountain? The fountain experiment there? The bluiness is the ammonia gas. The red water, because of the few drops of acid, is being sucked up, fountain experiment, as the ammonia here is dissolving really very easily into the water that's being sucked up. And fountain experiments can only be done, that kind of experiment can only be done if if the solubility is really very, very good. When the solubility is really very, very high. And ammonia has that solubility. You can see most of it now has been sucked from the bottom to the top. It will go on a little bit more and then it will stop. So while I just leave that for you to look at, I've been keeping an eye on this. And I've not yet got crystals. So I'm going to cool it down with cold tap. I'm going to run it under a cold tap to try and get crystals to form. I can't get crystals to form. So I'm just going to keep the cold tap running. While I cool it down with the cold tap is running on top of that boiling tube I was showing you, then I can run through a calculation. I can run through the calculation on the board. How can you work out the solubility? Well, the solubility, we had 2 grams of ammonium chloride, solid, and it dissolves in 5 grams of water. And what we're trying to work out is what temperature. What temperature? Right. Now, there we go. There, can you see? The crystals are starting to form. There. Those crystals are starting to form, and the temperature is 24 degrees. 24 degrees. Actually, temperature now has gone down to 23 degrees. 22 degrees. I think that cold tap did the trick. Can you see that? About 20 degrees. But we need a temperature. We need a temperature to do the calculation out. So, perhaps. Hi, welcome back. My phone stopped. So, we got this far. You look at that sentence. Where 2 grams of ammonium chloride, 2 grams, dissolved in 5 centimetre cubes of water. That solubility marks the boundary between the solution being saturated and not saturated. I wasn't happy with how that went, and therefore I'm redoing something because my phone went off, and I want to show you the following. I've set up 4 test tubes, and this is ammonium chloride. 2 grams, 2.5 grams, 3 grams, 3.5 grams. I've measured it accurately using a 2 decimal place balance. You can see the accuracy based on my masses that I've written down. And I've got there 4 test tubes, and what I've done is I've used small measuring cylinder, a 10mm measuring cylinder, and I've put 5 of distilled water in every one of these 4 test tubes. So 4 test tubes got 5 of water in them, and I've got different masses. So what I'm going to do is to put these masses into those test tubes and repeat the experiment 4 times all together. Yeah, my phone keeps going off again. So yeah, I'm going to repeat the experiment 4 times as follows. So 2 grams in the first test tube. 2.5 grams in the second test tube. 3 grams in the third test tube. 3.5 grams in the fourth and final test tube. Now I'm going to get a beaker and I'm going to fill it full of water. Now this is for the water bath. Beaker, water on there, and I'm going to start heating. Let me just get a few more things. Now I need to get the water hot and then stand these test tubes inside the water. Now look, these test tubes have got ammonium chloride, and at room temperature that amount of ammonium chloride in each of the 4 test tubes does not dissolve. This is the second one. Well, same with the other 4. None of them will dissolve at room temperature. But if I get the water inside the test tubes warm enough, then it will dissolve. Now, if I put all 4 in there, I'm going to lose track of which is which. So one thing which I can do is to label them A, B, C, and D. And that will give me the 4 test tubes in order when I put them in to that warm water. So here we go. Going into warm water. Going into warm water. Oh, that's too much water. Let's get that water less. Water. Do that again. 2 and 2 more. There. So I've got 4 of those test tubes in water, and the water's warming up, and as the warm water bath warms up the 5 centimeter cubes of water, I'm hoping that dissolving of that quantity of ammonium chloride will happen. Now let's take you through some calculations. Now if you find 2 grams of ammonium chloride dissolved in 5 centimeters of water, and we'll find out what temperature in a minute, then what will the solubility be at that temperature, whatever it is? Well, I want you to focus on this. We have to scale that up to 100 centimeter cubes, which is 100 grams of water. Remember, that is the industry standard. That is what we must scale to when we're talking about solubility. So when we do that, how do you go from 5 to 100? Well, you have to multiply by 20. So we have to multiply by 20. If we multiply by 20, like do the experiment 20 times bigger, then we wouldn't be using 2 grams, would we? We would be using 40 grams of ammonium chloride solid. It dissolves in 100 centimeter cubes or 100 grams. Every 1 gram of water is 1 centimeter cubed. So 100 grams or 100 centimeter cubes is exactly the same thing of water. And what we're going to find out is at what temperature that will happen. And therefore the solubility will equal 40 grams per 100 grams of water. And written in a more sensible way, 40 grams per 100 grams of water. That is how you work out solubilities. You have to scale up to 100 grams. Now look, here I've got a worksheet which I've flashed up onto my screen, and 2 grams in 5 mils I've calculated on the board is 40 grams per 100 mil of water. What that is, 2.5 grams. 2.5 grams would be 50 grams solubility per 100 mils or grams of water. 3 grams would be 60 grams per 100 mils of water. 3.5 grams in 5 mil would be 70 grams per 100 mils of water. And what we're hopefully going to do in a minute is work out what temperatures the crystals start to form. That is the boundary between saturated and non-saturated solution. And when we do that, then we're going to plot the solubilities. We're going to plot the solubilities on some graph paper. Now, let's have a look, see what's going on. There are those. Let's pick A. And I think that in test tube A, it's dissolved. Now, test tube B. B's that one. There's some solid down the side which I'm trying to push down. Perhaps you can see a little bit more closely that all of B has dissolved. That's B. Now let's pick up C. Can you see? The in C, I've got solid. I'm going to try and dissolve it by stirring it. Any extra solid down the side, I'm trying to get in to the test tube. Finding it hard to dissolve. Maybe I need to put it back into the hot water. Maybe. Put that back into hot water. And D will be harder still to dissolve. So perhaps we need to get the water a bit hotter in order to get those last two to dissolve. But those first two, A and B, they are cooling down. Now, I'm just going to grab a holder. 1 minute. Here, got a holder. I think that's probably better. You can see that I think a lot of it has dissolved. Stir it all up. Push down anything that crystals that are up there. That is C. And finally, let's pick up D. Now that was what was in there earlier. Stirring it up, get any solid down into the test tube, into the solution, getting it to dissolve, not dissolving yet. So I put it back in to get it to dissolve, get the water hotter. Now that water there is boiling. Can't get it hotter than boiling water. So I'm going to turn the Bunsen off. I think that should be hot enough for it to dissolve it. Let's try again. I'm stirring with the thermometer. I'm getting it to dissolve. Put it back in the hot water. There's still some solid left, it's not all dissolved. Maybe I can do that inside there. I'm going to, just to speed things along, just do something that's not so standard. And I'm going to heat it directly. I'm going to heat it directly. To get it to dissolve. Can you see? Heating it directly. Hope you can see. Right, okay. So that's a Bunsen burner. Heat it directly to get it to dissolve. There. There are the 4 test tubes. That last one, test tube D. Can you see we're looking at the solution really? We're looking at the bottom, and there we're going to look to see when we get crystals it cools down. The third one This third one, C, has started forming crystals at about 65 degrees. Look, 65 degrees. And can you see the crystals forming? So the third one is 65 degrees. C, 65 degrees Celsius. I'm just writing it down on the board, which you can't see. And I'm going to look to see when the others start to crystallize. Now the temperature here on the fourth one is at 90 degrees. Ah, there, it's starting to form. Look, crystals starting to crystallize at 88 degrees. Can you see that? 88 degrees, it started to crystallize. The first signs of crystals came out at 88 degrees. So D was 88 degrees Celsius. Now, keep your eye on those last two. Ah, there. That B, test tube B, is starting to form crystal at 48, 49, 48, 49. Sorry, parallax error. 49 degrees. So B is 49 degrees. B is 49 degrees. And finally, A, temperature there is 45-ish. No sign of crystals yet. And that might take a little bit of time for those crystals to form. I can cool it down with running water from a tap, which I am doing, which you can't see. Temperature is 40 degrees. No crystals yet. I hope you get the idea. I'm just going to leave that while I talk to you with the board. So these are my three temperatures: 49, 65 and 88. In this board, that would be B, C and D. 49, 49 there, B, 65 there, which is C, 88 there, which is D, and we've got that one to find out yet when it cools down enough to give us crystals. And can you see the four solubilities? Then we can plot them. Now let's see how we plot them. So carrying on, you can see we've got three results. We're still waiting for this one to form crystals, and the temperature is coming down. At the moment now, the temperature is 30 degrees. So when it starts to form crystals, we'll get a temperature, but how do you plot them? Now look, I've done a quick axis there. Solubility of ammonium chloride in grams per 100 grams of water on the y-axis. Maybe put an arrow here on the y-axis, and then let's plot D. D, can you see 88 degrees? Now 88 degrees was D, where the solubility was 70. So 70 at 88 degrees, that is D. You see, the solubility is 70 grams per 100 grams of water, and that solubility happened at 88 degrees. We saw crystals. Now let's do the others like that. 65 degrees, where the solubility of C was 60. 65 degrees, 60. That would be C. There. 65 degrees and solubility of 60 grams per 100 grams of water. And then B is 49. 49, and that would be 50. around 50, then that would be B. Now, it'd be nice to get A. Still not forming. Temperature is 30. I suppose with the room being 25, it's going to take me putting it under running water. Maybe you can watch. Watch me do it like this. Put it under running water. To try and get the insides cooler quicker so that we can get all four results. It will crystallize eventually. When the temperature inside is cold enough and the solubility is exceeded, then the extra solute will come out, and it will come out as crystals in a process called crystallization. There. Now it's starting. Can you see the crystals? Right, that's crystallization. So, what's the temperature? Well, temperature is 22 degrees. See that? 22 degrees. So, let's finish off what's on the board. A, 22 degrees. And we put that on the board, 22 degrees, 22, and a solubility of 40, 40 is there. So can you see, you get like a solubility curve. And that is the solubility curve for ammonium chloride done roughly. Now, if you have some graph paper, you can plot those better. You put the temperatures in here, the four temperatures, you know the solubilities based on what you started with in terms of solid in 5 mils. You've scaled up by a factor of 20 in order to get these figures per 100 mils or per 100 grams of water. And on that basis, then you can plot that kind of plot there as a solubility curve for ammonium chloride. I just wanted to show you how you would get one proper full solubility curve, and then I want you to be able to use solubility curves that are given to you to answer your questions however they may be asked. So what we learnt? Well, we learned from this experiment how to do a solubility curve. And you need to know that for solids and liquids, as the water temperature gets warmer, then the solubility increases. More and more solute can dissolve if the water is warmer. Conversely, if the water's colder, less and less solute dissolves. And these solubility curves, they mark this side of the curve where my hand is. This side of the curve marks where the solubility has not been exceeded. This side is where the solubility has been exceeded. And the line is where you get a saturated solution. So the line there separates the saturated solution from non-saturated solution. And they can be used in all kinds of ways. And one of the ways is to work out how much crystals, in terms of grams of crystals you'll get, if you cool something down and it starts to form crystals, how much crystals you'll get. And calculate here, if we knew the temperature, we could calculate the quantity of crystals that each of these test tubes, 4 test tubes, will produce. Can you see? This one has got more, but then we put more in. We put 3.5 grams in. Anyway, I think I'm whittering now, so let's let's end this here and we'll carry on with something else next time. See you then.